Welcome everyone. I have a quick video here today to go over the results of the midterm. In this video, I'll go over some of the midterm statistics in terms of grades across the class, and then I'll walk through the solutions to the exam. In terms of the statistics for this exam, we had 152 students take the exam. The average of all 152 students was a 66. The standard deviation across all students was 15. The median was 68. And the high score for this exam was a 99. So as you see here, about 81 students scored above the mean and 71 scored below the mean. Here's the breakdown by problem. Problem 1 was all the multiple choice and short answer questions. Question 2 was a digital logic, had a truth table and a logic circuit. Question 3 was a Fourier series question, and question 4 was a basically building a circuit at the Arduino and developing some code. So as a reminder, the midterm was worth 15% of your course grade. So if you did well in the midterm, congrats, keep it up. And if you didn't do as well as you wanted on the midterm, there's plenty of time to recover, right? So the final exam is worth 25% of your grade. So let's take a look at the solutions to the exam. For the midterm this semester, there were 2 versions of the exam. There's a version 1 and a version 2. So as a result, the answer key will have the version 1 answers shown in blue or sometimes in a blue box, and the version 2 answers will be in red or a red box. Let's take a look at question 1. So question 1 has a Arduino Uno, an NPN transistor, 2 resistors, and an LED. And the question is, based on how this circuit is wired, what single line of code, if placed in the loop function, which single line of code will either turn on the LED or turn off the LED? So to turn on the LED, we need basically no current flowing through this branch, right? So we'll need to effectively turn off the NPN transistor. And to do that, I'll set pin 7 low, right? So there'll be no current flowing through the base here. So the transistor will effectively be off. So all my current will flow through the LED and it'll turn the LED on. Now to turn the LED off, I want to turn on the transistor such that this is the path of least resistance to ground, and all of the current will flow through this section down to ground. This will effectively turn off the LED. So to do that, I need to turn on the NPN transistor. So I need to set pin 7 high. That'll effectively allow enough current to flow through this NPN such that the current can flow from the collector through the emitter, and that'll turn off the LED. So this circuit effectively acts as a NOT logic circuit. And let's take a look at that in Tinkercad. Okay, so here we are in Tinkercad then. I have an NPN transistor. I have the collector connected through a resistor here. The base is connected to pin 7, digital output pin 7. You notice there's no tilde here, so that's simply a digital high or low pin. And then the emitter is connected to ground. And then in the same chain, I have this connection through a resistor, a current limiting resistor, to my LED, which is then connected to ground. So in my code, I have to call pin 7 as an output. And if I write pin 7 low, if I write it low, that'll turn off the transistor. So I should see the LED illuminated. So let's go ahead and run that. And lo and behold, the LED is illuminated. Now, if I write this pin high, that will turn on the transistor, allowing current to flow from the collector to the emitter, and that'll be the path of least resistance. So we should see the LED turn off or remain not illuminated. And there we go. Okay, question 1b, this is a coding question, and specifically it's a processing code question. So in version 1, we have a declaration of integer x and y equal to 10, we plot an ellipse, and then we increment x and y by 1. However, in the draw loop, we reinitialize x and y to 10 each time, right? So as a result, this ellipse will stay in the center of the screen, and it'll have a constant width, in this case, a semi-major and semi-minor axis of the ellipse of 10. So version 1 has an answer of B, and that's what that looks like if you were to run the code in processing. I encourage you to do that. You'll basically see this ellipse in the center of the screen. Here I took a snippet, so you're just seeing a portion of the screen. But this guy will remain in the center of the screen with a constant semi-major and semi-minor axis. Now, version 2, on the other hand, we declared int x and y as global variables before our setup function. And then in draw, we once again increment x and y by 1. So as a result, for version 2 of the exam, now you have a circle in the center of the sketch, but each time you go through the draw function, the semi-major and semi-minor axes are incrementing in size. So you'll see this guy get larger and larger and larger as you go throughout time in terms of executing the sketch. So for version 1, the answer should be B, and then for version 2, the answer should be A. Okay, question 1C. This is a multiplexer question. This is pulled effectively straight out of Lab 1. And the question is, if I have a 16-input multiplexer, how many select lines will I have? Well, if I have a 16-input multiplexer, that's 2 to the 4, so I'll have 4 select lines. So the answer for version 1 would be 4, and the answer for version 2 of the exam would be 4, right? So C or E, the way they were set up on the exam. One part D, this was converting between base systems. So in both versions of the exam, you were provided a decimal number and asked, what's the binary equivalent? So you could go through, right, divide by 2 and look at remainders or not remainders, right, for zeros or ones. So if you had version 1 of the exam, you had a decimal number of 202. The binary equivalent of that will be 1100, 1010. And it doesn't matter how many leading zeros you have, right? You could have an infinite number of leading zeros, technically. And for version 2 of the exam, you're asked, what's the decimal number of 240? So for the binary equivalent of that, rather, is 11110000. Question 1E, this is asking about even and odd functions. If you recall, this was in the Fourier series lecture. And version 1 of the exam says, well, if the analog signal, the continuous time function, is even, it'll have only cosine or sine terms. Well, if it's even, it only has cosine terms, right? Because it's symmetric about the y-axis. On the other hand, if the function is odd, it'll have only sine terms. So that would be version 2 of the exam. Question 1F of the exam, this is an analog to digital conversion question. Specifically a SAR, successive approximation register question. And there are multiple ways to solve this problem. The most direct way would be to implement the SAR search algorithm. We went through an example of this in lecture where we were looking at a scale and we had a certain number of uniquely valued weights. And we said, what's the minimum number of tests we'd have to run to actually determine the weight of something? This is effectively the search algorithm that's used by the successive approximation register ADC. So ideally, you would go through the SAR search algorithm to solve for the binary code, not the decimal code, the binary code. You could also implement the equation relating the approximation of the voltage, what the analog to digital converter is interpreting or approximating the voltage as. You recall that was equal to the input voltage divided by the full scale range voltage, all times 2 to the m, and then you'd have to divide or round down rather. Or you could do the same thing times 2 to the m quantity, then minus 1, and round up, right? So either way will give you the same answer, but the spirit of this question was actually looking at the SAR search algorithm as we see here. So for version 1 of the exam, we had a input of 2.9 volts, and when we went through our search code looking at, was it above or below 2.5 and continuing from there, we ended up with a code of 10010. And the decimal equivalent of that was 18. So if you gave me 18, you got about half credit on this problem, but the question did ask for the binary code. That would give you the full credit. And then the same thing for version 2 of the exam, we had an input of 1.9 volts. If we went through either multiplying by 2 to the m and rounding down, or 2 to the m minus 1 rounding up, or preferably going through the search code, you end up with a binary code here of 01100, right, or decimal equivalent of 12. So I needed the binary code for full credit, and the decimal code gave about half credit for this problem. Question 1, part G. This is a sampling and aliasing question, ultimately linking back to analog to digital conversion, but really a sampling and aliasing question. Right, so I say each of these 4 signals at right, they're each shown for 1 second. So a 1 second long sample or section rather of the analog signal. And if we sample those at 5 hertz for version 1 or 14 hertz for version 2, the question is, which ones will alias? Which ones will alias, right? So this first signal, this looks like it's about a 1 hertz signal. This is about a 2 hertz signal, and so on. And if I'm sampling at 5 hertz, well, the maximum frequency content I can see based on what Nyquist tells me is 2.5 hertz, right? So for version 1, only these first 2 signals will get through without aliasing. And if I sample at 14 hertz, then the maximum frequency content I'll see is 7 hertz, right? It's always half of that sampling frequency is the maximum frequency content I'll see based on the Nyquist theorem. So for version 2, the answer would be C. I get X1, X2, and X3, punch those through with no aliasing, but I'm not sampling fast enough to see this signal X4. And then the last question here for last part of question 1 rather, 1 part H. You're provided this snippet of code, and the question is, what happens, right? Does it have any errors? Will it compile? And based on how the code is set up, the student is trying to compute the average of 4 analog reads. And this is actually a very important problem that you should take note, foreshadowing for the future. This is effectively doing what's called a running average or a moving average. So basically digital filtering in terms of code and running through this loop, although we'll get into that later in the semester. But here the student's trying to compute the average of 4 analog reads, and in fact there is nothing wrong with this code, right? So this code will correctly compute the average as desired by the student. So version 1 and version 2, the correct answer was that, in fact, yes, this code does correctly compute the average. Question 2 of the midterm has 2 parts, A and B. And the spirit of this question is really asking about digital logic circuits, and truth tables, right? So for both versions of the exam, you're provided the same setup here. You have this automotive safety circuit, and the buzzer should turn on. So the buzzer should be high, or 1, whenever a door is open, or when the key is in the ignition and the seatbelt is not buckled. So whenever the door is open, so whenever there's a 1, the buzzer should be a 1. So if you notice the completed truth table here, anytime the door is open, a 1, the buzzer will be a 1. The buzzer will be on. And otherwise, if the door is closed, so it's a 0, then the question is using the or statement. So or when the key is in the ignition and the seatbelt is not buckled. So that would be this condition here, right? The door is closed, but the key is in the ignition and the seatbelt is not buckled, right? So we have a buzzer alerting the user as well. So for both versions of the exam, you should end up with the following truth table. Part B says, based on that truth table, and based on the requirements of the safety system, complete this logic diagram. So draw the logic circuit by wiring the inputs. So the seatbelt S, key K, and the door D. And then we wire these into our logic gates here. So let's take a look at what that is telling me. So here I have the, what is S? The seatbelt going into a NOT gate, right? And then I have the key and the not seatbelt going into an AND gate. And the output of that is going to an OR gate, where that OR is getting ORed with the door, right? So we have the door, OR, not seatbelt, and the key is in the ignition, ignites or turns on, right, the buzzer, sends the buzzer high, and alerts the user, hey, we have a problem here. So for both versions of the exam, this is the correct logic circuit in terms of wiring. Question 3 of the midterm, this is a combination here. We have Fourier series and Fourier transform question. And then part B and C were really questions on sampling and aliasing, and then implementing that in code for part C. So for version 1 and version 2, you had different plots, slightly different plots of time. And for part A, you had to sketch the amplitude spectrum plot on the following graph. Now, you are graphing this on paper, but to illustrate the solution to these exams, let's take a look at this in MATLAB. So I'll take a look at version 1 of the exam first. If I go ahead and run my code, I end up with the following plots of interest here. So here is the original sketch that you saw on the exam. And the question was, okay, basically run an FFT, in fact, a DFT of this signal and give us the amplitude spectrum plots, right? So to begin this problem, we need to appreciate that there is a fundamental sine, or in this case cosine wave, that my final plot is plotted on top of, right? There's a higher frequency component as well. But there's this 1/2 hertz frequency component. I know it's 1/2 hertz because it completes 1 period in 2 seconds. And that fundamental component's going to go basically right through the middle of the blue curve that's on the exam. Furthermore, it's clear that there is a DC offset to that component, right? So that 1/2 hertz sine wave or cosine wave is offset by an amplitude of 5. So that'll get me this red curve right through the middle of the curve on the exam. Now, on top of that, there is a higher frequency component riding on top of this 1/2 hertz fundamental frequency component. Now, this higher frequency component, this will be at 4 hertz, right? If you look, there's 1, 2, 3, 4 periods in a second, so that'll be 4 hertz. And this, you'll notice all the peaks line up, right? The peaks from the magenta and the green, the magenta and the blue, rather, curves here. And so I need to look in terms of a Fourier series at the addition, at every moment of time, the addition of the red and magenta curves, and that will give me the resulting curve here. Okay, so if I add this fundamental frequency at 1/2 hertz, if I add that to this 4 hertz higher frequency component, I'll end up with the following plot here, where now the red curve is the summation of the two, the Fourier series of the two, and it's landing right on top of the original blue signal, right? So I know all of the components in terms of their amplitudes and their frequencies, and as a result, here is what we are looking for part A, right? So I have a 0 hertz component, a DC offset at 5. I have a 1/2 hertz component at a magnitude of 3. And so if I could look from, say, peak to peak values, I get the magnitude there, accounting for the DC offset. And then I had a 4 hertz component with an amplitude of 1, right? So this plot at right, sketch by hand, is what we're looking for part A of the exam. And of course, that's version 1. So let's take a quick look then at the numbers for version 2 of the exam. Okay, so here's the same idea. Here is the original plot. This is what you saw on your piece of paper. And the question was, well, what is the amplitude spectrum plot look like for that guy, right? So here we have our fundamental component in red again, right? There's that fundamental component going right through the middle of that plot. Then we have our higher frequency component coming through. Okay, it looks like 1, 2, 3, about 3 hertz for that higher frequency component, and it looks like we still have about 1/2 hertz, I guess, for the original component of red. And when I add those together at any moment in time, I end up with the following plot here. So the question then was, what's the amplitude and amplitude spectrum plot look like? And here's the answer for version 2 of the exam. So DC offset of 4, a 1/2 hertz component with an amplitude or magnitude of 4, and a 3 hertz component with a magnitude of 1. So this would be for version 2, question 3, part A. Question 3, part B, this is a Nyquist question, right? So based on those frequency components that we saw for in part A, what is the minimum sampling rate required such that there is no aliasing, right? So Nyquist tells us we have to sample at greater than 2 times that maximum frequency component. So for version 1 of the exam, we had a 4 hertz component, so we have to sample at greater than 4 hertz times 2, which will be 8 hertz. And for version 2 of the exam, we had a 3 hertz component, so we had to sample at greater than twice that, or 6 hertz. And then lastly, for question 3, we have part C here. It's basically saying put that requirement for sampling frequency into code, so give us the appropriate delay in terms of microseconds, right? So if you're sampling at greater than 8 hertz, you need a delay less than about 125,000 microseconds, and 6 hertz would be a delay of roughly less than 166,000 microseconds. Okay, so the math there is saying that I'm sampling at some rate here, right? I've got this analog read going on in this code, and I'm going to sample fast enough so my interval between samples will be slow enough that I will not have any concerns in terms of aliasing. Question 4, last question of the exam, has two components, 4A and 4B. 4A is asking you to wire up a circuit. So very much the case of what we've been doing in lab this semester. And then 4B says, okay, based on the requirements for the circuit, write the code that will drive the circuit, force the circuit to operate how the user requires the circuit to operate. So here we're using a cadmium sulfide photoresistor, and we're going to use this as a motion detector, right? So it's going to be sensing ambient light in a room, and if it gets enough of a change of ambient light, i.e. enough of a change of resistance on the sensor, i.e. enough of a change of voltage on the analog to digital converter, it'll tell the user, hey, there's motion detected, right? And we could use that for a variety of reasons in terms of the overall system, right? So the Nest thermostat, I have one of these at my house. It has a motion sensor operating under similar principles. So it tells, hey, whenever someone walks in the room, it actually tells me what the temperature is, which is quite nice, right? So part A says, okay, you have all the components in your lab kit this semester, and you have an Uno, and then I give you this photoresistor. It says basically wire this thing up to read on pin 3 for version 1 of the exam, or pin 5 on version 2 of the exam. Now, this is a motion detector. This is not a light on, light off room detector, okay? And that's highlighted particularly in part B, where I say there's a change of more than 1 volt, okay? So you need to use analog pins here. So you need to be wired up into analog A3 for version 1 or analog A5 for version 2. And then you'd also need something like 5 volts coming through, and then you need a voltage divider to actually measure a change in resistance of this photoresistor, right? So if you don't have a voltage divider, if you just have the photoresistor, you'll always get the 5 volt drop across that guy no matter what. So the requirements were voltage divider, so power, 5 volts, ground, voltage divider, and then reading the output on these analog pins. Part B then asks, go ahead and write some code to drive the operation of this circuit. And you had every 50 milliseconds for version 1 and every 100 milliseconds for version 2, you had to perform the following, right? So every 50 millisecond interval, perform the following. So you want to read the voltage across the photoresistor and print the corresponding ADC code, right? So in this case, I'm looking for the code 0 to 1023, not the voltage, not some interpretation of the voltage. Print the actual ADC code 0 to 1023. Then go ahead and alert the user by serial.printing or serial.printlining, motion detected, if the voltage has changed more than 1 volt. Okay, so now you need to account for voltage as read by the Arduino. So you have a full scale range of 5 volts. And you have a 10-bit analog to digital converter, right? So 1 volt change is going to be roughly 1023 divided by 5, or about 204 ADC codes. The other key here is that it's a change of 1 volt, not one direction or the other, but both. So you needed to do something in terms of absolute value or square rooting or something to account for a voltage going from, say, 2 to 3 volts or from 3 to 2 volts. So you had to look at it in both directions. So let's take a look at Tinkercad and take a look at this circuit in a little more detail. So here's my circuit. I have a Arduino Uno. Here's the photoresistor. In this circuit, I ran power to a power rail on this board and across, and then I ran a ground rail as well. You didn't have to use a prototype board on the exam. You could just wire it in free space. That's fine, but for the purposes of going over the solutions, I've wired it this way. Here's my voltage divider. So I have power coming through to a resistor, going through a photoresistor and to ground, and I'm measuring the output of that voltage divider on analog pin 3. So I'm looking at version 1 of the exam here. This would be the same thing for version 2 if you'd wire that up to pin A5. In terms of code, there's many ways to code this up. So I initialize a global variable old, and I initialize that equal to 0. In setup, I have pin mode A3 as an input. Now you don't have to do that. Okay, the analog to digital converter pins, they can only read in inputs. They're analog to digital converters. So you don't have to put that bit of code in there, but I did just to be complete. And you need a serial.begin with some rate. Most people chose 9600. I think a couple chose 115.200. That was fine. But you had to have a serial.begin with some rate. Okay. In the loop command, here's how I attack the problem. I start with a delay right off the bat. So go ahead and delay 50 milliseconds, right? So remember, delay is in milliseconds. You could also use delay microseconds. That would be 50,000 in this case. I go ahead and read the value. So I have an analog read of 3. And I print that value right to the screen. Because remember, I'm asked to print the code here, right? So I'll get some number between 0 and 1023. I then run through and I look at the difference, old minus value. Now I have to actually run through the code one time. The first time rather, I'll have 0 and then I'll actually rename old later. So I have a print of value and I look at the difference between old and the current value and I take the absolute value of that because I could be going up in voltage and I could be going down. Now I have an if loop here. I say if that difference is greater than 200. And if you wanted to be exact, it should probably be more like 204, right? It's 1023 divided by 5, right? But I said, if it's greater than 200, you have a 1 volt change. And if that happens, go ahead and tell the user, serial.println, that motion was detected. I'll run that here in a second, look at the serial monitor, but then I reassign old the current of value. And I go through the loop, and every 50 milliseconds I make this comparison. Let's go ahead and run that guy and take a look here, okay? So here I've got the photoresistor, and I can change the amount of light, incident light one way or another. And if I sort of slowly move this guy over, you'll notice I never get a motion detected, okay? Because I never get above 200. And obviously these output codes here are going to be dependent on how you have your voltage divider set up. That wasn't part of the exam, that's fine. But if I could force this thing to have enough of a change of greater than 200 ADC codes, watch what happens. So I move that guy over, boom, motion detected. Okay, if I get it over 200, I get motion detected. So that'll tell me if something has occurred and somebody's walking through the room there. So that was the requirement for question 4, part B. You had to wire it up in part A and then write the code in part B. Once again, if you have any questions on the exam or how things were graded, take a look at the video and then come chat with me or Dr. Harish during our office hours. We admit that we are super space human. We do make mistakes every once in a while, but if we do, bring it to our attention. We'll solve it right away and get everything squared away so that you're all good to go. Okay, thanks a lot.